So again, the idea is that we want to choose some sort of data source and get an average over a wider area. So not just sample a single point, but sample a whole region. As we've seen, there's quite a lot of different data sets available on Earth Engine. The ones that we want to target for this kind of exercise are ones that are not too high resolution. If you want to get the average of a lot of Landsat data over a very big area, that is really a lot of data. But you think of these climate data sets that are only 30-kilometer resolution, something like this, you can cover a very big area with a smaller amount of data. So it's easier to download it and process it and make maps. So we are going to go back to this ERA5 data. Oh, maybe we can't see the actual data set here. I will go update this link in this GitHub later. Oops. Control M. Let's just reload this. There, it's back. So the ERA5 data, this is what we want to work with today. We've been looking at it on the Google website. Okay, but maybe it's just because their website is down. So the ERA5 data isn't only monthly data. We also have hourly data. So they produce hourly data not just over every part of space, but also all through the atmosphere. So you have these pressure levels near the surface, all the way up to the edge of the atmosphere. And it's hourly data, and now it's going from 1940 all the way to the present. So there's really a lot of data there. So we want to, in this exercise, generate a time series, so like what we did with the rainfall data, but also generate some maps. And hopefully, if we load this in again, I have to start this setup again. Put in my credentials here. And if I get this Mount Everest elevation, then this should all be working. So this time for a study area, we want to choose a wider area. For example, here I have a map of the Trishuli catchment. So this is where we've mostly been working in the last few years. And this is a pretty big area covering from just outside of Kathmandu up towards Langtang and also over crossing into the Chinese border. There are a lot of different ways you can make such a geographic box. One of my favorite ones is this website, geojson.io, which I guess I have to fix that link too. If you open up this geojson.io website, it should come up with something that looks like this. And what this lets you do is you can scroll to anywhere you want on the Earth. For example, if this loads up here, we can zoom in and make a box over Nepal. You can select different kinds of polygons, for example, a line or a point or a box. And I'm going to just test this by drawing a rectangle. It's a little bit slow. There we go. So I can click and drag a rectangle, and what this will do is it shows me this structured data format here on the right. And this is called a GeoJSON file. It's something that is often used to pass around data, geographic data, in a very structured way. so that computer programs and different kinds of computer programs all know how to work with this data. So it has a very well-published structure that it always has exactly this kind of bracket and then some line telling you what it is. Inside a feature collection, we have some features, which we know is now a geometry with some coordinates. So it's structured like a dictionary. You have these little pieces that then correspond to different attributes. And this can be a really nice and fast way to draw a polygon, and you can copy and paste this code as GeoJSON. And if you save that or download it, you can use that directly in Earth Engine. Now, what I've done is I have instead, I've basically copied the output from geojson.io. We can look at this here, what is actually being loaded here. If I run this, you can see that my feature collection for Trishuli is also one feature that has a name, and it has some features which inside of them give me some perimeter and some geometry. And this is a polygon with some amount of coordinates, a lot of coordinates, right? It's a very complex shape, so you need coordinates for every time the line changes direction, right? So it becomes a very complicated polygon. But this format is exactly what is coming out of here. And that we can read in with GeoPandas. So up here we loaded in one new library called GeoPandas. And that is basically a version of pandas like we've been using to work with table data, which knows how to handle geometry. It knows what a circle is. It knows what a square is. It knows what the distance is between two different points. So it has some knowledge of geometry and coordinate systems and map projections, so you can use it for any kind of geographic data. Which means we can read this file directly, and since GeoPandas, it's just reading straight off of GitHub. We don't have to download the file, I can read it directly. And since it has this nice structured data in there, it knows that my polygon has some area and some perimeter value and some other attributes that came from my watershed file, and then it has this long geometry string. And this geometry is exactly what we need to give Google Earth Engine to tell it, this is where we want to do our analysis. This is where we want to get our averages. This is where we want to collect data. Alternatively, if we want to use a simpler file, we can look at this one. This should just be a small box covering the Trishuli. So this is a much simpler polygon. I can even copy and paste it and put it in here, and we can, and we can see that this will zoom in on my region. This is now my bounding box. Maybe we can try that also with the other one and see what that looks like. If I copy all of this and put it into my geojson.io, it should now give me a nice view of my watershed. So this GeoJSON file, you can open it up with this great website, geojson.io, and you can even save it into some other kind of format. So those of you who have ever done a GIS class or something like this have probably worked with shapefiles, right? This is one of those standard data formats for working with polygons or other kinds of geometry. So once you load it in, for example, from this long string of dictionaries, you can convert it into KML, which is for Google Earth, or shapefiles, which is for Esri or any other kind of GIS software, or you can keep it in this GeoJSON format, which is useful for working with online tools, not just Google Earth Engine, but also Copernicus browser, the one we looked at this morning, or other tools. So we can see that now our geometry is quite a lot simpler. We've saved these two things as our Trishuli outline, and our test outline. So that's just the whole watershed and then the box surrounding the watershed. Google Earth doesn't know automatically how to translate this GeoPandas data into something that it knows how to ingest. We have to give it a slightly special format, but thankfully GeoPandas has exactly the tools to read it. We just have to do a sort of funny little conversion. And this little block here is doing exactly that for us. We're creating an Earth engine geometry, and instead of a point, like this morning when we did Kathmandu or the other locations, we did an Earth engine geometry point. Now it's a multi-polygon, which is made up of the geometry of my Trishuli outline file. And I do the same thing for my area of interest. And if I run these, I can see that now they are giving me these Earth engine coordinates. Earth engine get info. It knows how to deal with this data. And we can now work with this with our other Earth engine code. So those are now things that Earth engine understands. Does that make sense? It's a little complicated. How many of you have had GIS classes before? Yeah, okay, so many of you. So you've seen what polygons and points and lines and these kinds of things. Earth engine can also work with all of these, but you have to give it the data in the right format. All right. So the reason why I have not just my watershed outline, but also this much simpler outline is because it can be a lot faster. If you don't have to use these little points to check every single pixel, is it actually inside my watershed or not? If you only have to check these 4 corners, it can go a lot faster on the server when it's doing these aggregations and giving you back data. So that's why we have this more simple polygon as well to speed things up, basically. So for the climate data that we want to work with, we are going to look at ERA5 data again. So this is the same data we looked at before. The data on Earth Engine comes in 3 different resolutions. We have daily data, monthly data, and even hourly data. So the monthly data, this is what we use to look at temperature and precipitation trends. And it goes from 1979 to 2020. The daily data has basically the same temporal coverage, except now it is every day instead of every month, and we have the same attributes. The hourly data is the one that is the most up to date. So this one goes all the way from 1950 until like a week ago, right? So it has a 1-week latency. However, this data set is then huge, right? Every hour is a lot more data points than every day or every month, right? Hundreds and hundreds of times more. We also have a lot more bands. So the hourly data has all of these raw outputs from the from the ERA5 data. Any kind of climate parameter you might think of, it's probably in here. We have evaporation, we have snowfall, snowmelt, surface heat flux. There's, I think, 80 variables or something in here. So not all of those are available in the monthly and daily aggregates. So sometimes you might have some variable that you really want to look at on a daily scale, and if you want to do that, you're going to have to sum it up or average it yourself. So the raw data is there on Earth Engine, but you have to, they don't keep it prepared. These ones people use more often, so they have some averages ready. So not everyone has to go to the hourly data. We can take a look at how different these sizes are. So if I load in my hourly, daily, and monthly data as hourly, daily, and monthly, I can get their sizes. And this will tell me how many values I have or how many individual images I have for each of these data sets. Monthly, this is the 500 data we worked with before. Daily already gets quite big, right? 15,000. And then hourly is something crazy, right? 670,000 different images. We have access to all of those images just by typing this one line in. Whether or not we really need to work with hourly data would depend a lot on what kind of phenomenon you're studying. A lot of things will only change from day to day, right? Hour to hour, the temperature of the air on average is not going to change that much. So depending on what kind of analysis you want to do, you can choose the kind of time resolution. For comparison, this is the daily precipitation data from CHIRPS. So this is 30-kilometer spatial resolution, and this is 5-kilometer spatial resolution. The time coverage is pretty similar. So depending on if you need something really high resolution or you're fine with something lower resolution, you can also choose between different data sets that do the same thing. Both of these have rainfall rates. It just depends how much spatial resolution you have and which kind of data set you want to work with. So for the rest of the notebook, I think I'm going to use this monthly data just because it runs a lot faster. But you can switch any of these lines of code to use the daily data or the hourly data, and they will run exactly the same way. They will just take quite a lot longer to run because they need to collect a lot more data. So, in the same way that we did in the last exercise, we're going to define some function to export our time series. You can see that I've made this a little bit more complicated than last time. Before, we just had one thing. It was just getting the mean of 1 point. Because the mean, the max, the sum of 1 point, it's always going to be the same thing, right? But as soon as we start working with a wider area and a wider region, then we can get the maximum, the minimum, the mean, the sum, all of these things, they start to have a real meaning and be useful for understanding what's going on in our catchment. Otherwise, the syntax is exactly the same. I'm going to take some image collection, so some set of images that have rainfall, precipitation, whatever, some geometry that I want to use to aggregate them, and some variable that I'm interested in. So ERA5 has 50 variables in it. I have to choose which one I'm actually interested in. And then it will get me a mean, a maximum, a minimum, and a sum, and store all those things, and give us back, do this for loop, going through all of this data that we just covered, and make it into something that's much easier for us to work with. And I think I'm running this on the monthly data, just so it goes rather fast. Very fast, actually. If we can now look at this, means this should now give us about 500 values that are a monthly mean covering my area of interest, which is the whole Trishuli catchment, using the total precipitation variable, and that ran extremely quickly, right? So we now have monthly average precipitation for the entire catchment just with that little command. We can also look at the sums. This should be different. We see that our precipitation sums are a little bit higher if this will run. There. So then this is the average or the aggregated precipitation instead of just the average. And we can plot those. So this is just making the same kind of plot as before. We make a figure with 3 axes, 1, 2, 3, with our matplotlib library, which gives us plotting functions, giving us 3 axes and some figure size. And first we're going to plot the minimums of every month. Then we're going to plot the average of every month and the maximum of every month. And each of these I give a label to. And we can see that we have now from the 1979 until 2020, we have our average and our maximum and our minimum and our sum of our monthly rainfall. And you can see the monsoon peak in there. as well as the much drier periods. And you can quickly pick out that there's maybe been a few strong monsoon years recently that have a very, very high average precipitation over the Trishuli. Does that work for everyone? Yeah, makes sense? The only difference we've gone from here is we went from one point to going over a whole area. So we're using way more data, but we end up with something that looks quite similar, right? And you could do this if you have two watersheds next to each other. You compare those time series and see how different they are. Just switch the code of which geometry. For example, if I change here, my area of interest, let's see what did I define these as? Area of interest is my complicated geometry, and area of interest 2 is my simple box. And I can run this again. The only thing I need to change is what my geometry is, and it should give me something quite similar. But instead, I'm aggregating over a larger area. And I already see that I lost one of my high monsoon peaks there. So there's been a slight difference in this wider area versus just this catchment. We can also, since this is running quite quickly, we can take a look at how this looks from chirps, which is a much higher resolution data set. I'm just commenting this one and uncommenting this one. And we can run this again for the chirps data. And it should go a little bit slower since it's 5-kilometer data instead of 30-kilometer data. So it's 6 times as much data it needs to process. But at the end, we should be able to make the same chart. Aha, or maybe not. Okay, so this is good. When you try to work with too many elements, if you have too big of a time series, it doesn't want to give you 100,000 values. It's like you're going to overload our server if you try to get these hundreds of thousands of things. They have a rate limit. So we can't go directly to the chirps data with 5,000 elements. We can, however, export the data. So we could run this same command and export it to our Google Drive, and that will run with no problems. But for the interactive shell, we're limited to less than 5,000 items whenever we go through. So that explains why I had a comment in there. Let's run that again. And now that we have also something like our minimums and our maximums, we can also look at, for example, the range. We can look at the maximum versus the monthly, or the minimum, which months have a bigger variability. So some months have a really, really low difference. The difference between the maximum precipitation sum and the minimum is almost 0, right? So there was almost no precipitation, versus in the monsoon times, you have these really, really big differences between the monthly minimum and the monthly maximum. And again, this is aggregated over a whole watershed, right? So this means that this is not just for one single point, but it could be covering a place that gets lots of rain and a place that gets less rain. So during the monsoon, the sort of distribution of the rainfall throughout the catchment can change quite a lot. And that's what's reflected in this minimum minus the maximum. So one other thing to look at with this then, if we see that there's this range of more than a meter difference between the highest and lowest rainfall pixel within a catchment, is where are those high rainfall areas and where are those low rainfall areas, right? You don't just want this temporal resolution, you also want to know where this is in space. Is there some spatial pattern? When we do this kind of time series analysis, we don't often see that map, right? We're aggregating the space down to one time. The other option is we aggregate the time down to one spatial pixel, right? So instead of getting one value for each map, we get one value for each location, averaging over time instead of over space. And it can be really helpful to look at both of those things together. And all we have to do is go back to these reducers, this same reducer. This will work over space and give us one monthly average over each pixel of our watershed. And since this is a rather small area, we can also download this data directly. We can use this get info. It's not too big of a data set. And inside of there, we have this sort of structured data like we have before. And we can pull that out. So let's look quickly at this on a map before we export it. And then we're going to try to download it and make our own map with it instead of relying on the web map. This is what that long-term average precipitation looks like. This looks very similar to what we looked at before, right? So what we're interested in is what's going on in this area. And you can see that at this ERA 5 spatial resolution, it's not that many pixels that we have to download. It's only going to be, I guess, once this catches up. It's not so much data that we have to download for such a small catchment at 30 kilometers spatial resolution. So this is what the sort of native spatial resolution looks like. It's only 4 or 5 blocks per covering the whole catchment. We can also look at this maximum. So this is the similar stuff that we did this morning, looking at these maximum total precipitation maps and looking at these minimums. I'm also going to put this trend map up there, so we can look at the trend in the monthly precipitation. Again, this is the same kind of maps that we were generating before. And what I want to do then is, let's see, now that we have our precipitation trend maps, and I've put them with a little bit more of a useful color, with blue as increasing precipitation and red as decreasing, I want to compare this also to temperature trends. And all I have to do if I want to switch to working with temperature data is switch which variable I'm working with here. So my first regression was using this total precipitation. And now instead, I'm using this air temperature. So we can compare this. It should also run really, really quick and see what the air temperature is looking like. So this is all stuff that we did in the last exercise, right? We made these trends, we looked at these maps. The next step we might want to do is go beyond working with just this web map data and be able to download it and work with it on our own computers. And this is also something that you might have to do if you want to do a really complicated calculation, or if you want to work with the daily data or the hourly data instead of the monthly data, right? We're going to hit this rate limit of 5,000 items. We can't do too complicated calculations here in this web map. So we might have to run these, run this data on sort of an offline setting. Thankfully, this is really, really simple also. We can run any sort of task. We can export any of these data sets that we've made to our Google Drive. So this function is just setting up this export with all of the different things that you need to give it. You want to give it one image. So for example, our trend, our monthly mean, whatever you might have. A CRS, so a coordinate reference system. For those of you who have not had a lot of GIS, this is how your computer or your spatial analysis program knows how big each pixel is and where your image is located on the globe. You need some sort of reference system to know how to convert data from the globe, which is a sphere, to a nice flat square, right? So whenever we're getting data, our computer doesn't actually show us a sphere, we get some flat map. And how we convert from that sphere to this square map is what we get in this coordinate reference system. We also need some scale, so how big is the pixel that we want to export, how big is the data we want to export, and a region. So this would then be our spatial region. Do we want to export the whole globe, or just our watershed, or just an area around it? It's very, very flexible. And it will then, this just sets up from these arguments that we give it, this task, and it will export this image to our Google Drive. So if I run this, we can then export my annual temperature trend, so exactly what we have here in this web map. My coordinate system is this EPSG code, which is basically just the latitude and longitude. This is a very simple latitude and longitude grid that is commonly used. I have some file name, so I'm calling it my monthly temperature trend from 1979 to 2023. I set my scale as my 27,000 meters, and that's exactly the scale that I get from here. So my ERA 5 data says my data is 27,000 meters in size, so I'm exporting the native resolution. And I'm using my Trishuli area as my area of interest. Now, so both of these tasks takes less than a minute, right? So we can do a lot of cool stuff and we can get these trend results really fast, not just as these web maps for exploring, but also for downloading and making our own maps offline. The nice thing, I guess we're already here, we've already done our visualization. If we wanted to download this whole original data set, it would be hundreds and hundreds of gigabytes, right? Whereas when we just download this little piece, it's quite small. It's less than a megabyte, I think, right? 161 kilobytes. And it runs in less than a minute, so we can very quickly access and do analysis on these huge data sets without using our own computers. Once we have both of these things set up, once we have now our rainfall time series, and we've also downloaded this rainfall map or this precipitation map, we can try to put them together. Often when you make such a report or a chart, or if you want to make some analysis over a whole watershed, it's useful to show the spatial pattern as well as the temporal pattern. So I'm going to get some higher resolution rainfall, just so we have a slightly nicer looking time series that's a little bit bigger. I'm taking my CHIRPS rainfall data for the last 2 years, so 2024 to 2026, over Trishuli, and I'm getting the precipitation data. So I can plot this, and this will be a little bit nicer looking than the ERA 5 data, because we have a little bit of a tighter spatial resolution. But we can say, okay, we have our Trishuli rainfall sum for a couple of years. I've done a couple of little fancy things to make the dates look nicer, right? If I go up here to my axes, I've made my labels a little bit bigger. I've rotated our x-axis just to make the chart look a little bit nicer. And now we have something that looks nice, like, right? This could go in a report about what's been going on in my study watershed over the last couple of years. On the side of that, we can also run the long-term mean. So this is now my chirps 5-kilometer data. You can see I'm using the same coordinate system, calling it Trishuli rainfall mean instead. I'm using a much smaller spatial scale. Instead of 27,000, it's 5,000, but this same region of interest. So this is running. It should go fairly quickly as well. If I refresh this, it should show up on my tasks list. And I don't know that it's going to run in less than a minute, but it might take 2 or 3 minutes, but it will still go pretty fast. And I'm running the same kind of analysis over just the higher resolution data. Once you've exported that, you can download it from GitHub or straight from your Google Drive. I think I can open the version that I saved here already. Let's see if I find this. So geodata, Trishuli rainfall mean. Just so we can see what this looks like. It is over this Trishuli area, and it's a much higher resolution, right? So we have this 5-kilometer data instead of 30-kilometer data, but we're still constrained to being just a little bit bigger than our box. So it should give me a square that includes sort of every pixel that's touched. If I zoom way in here, this little corner of Trishuli goes up to this line, so I have this little bit of buffer there. Now, we can see if this is already finished running, and just to have an idea of how long it actually takes to export. It also took, 1 minute instead of 52 seconds, so still pretty fast. Once we have this data as a raster, we can, of course, open it in QGIS, like what I just did, but we can also open it in Python. Python isn't just for working with time series data and tabular data. We can also work very well with images. So for this, I have one new library called raster.io, which is raster import output. It's basically just for loading in this kind of geographic data. So TIFF data, this kind of data that you might have worked with before, that is an image, but also has some spatial reference. If you've downloaded the data, you can open it like this, but raster.io is also happy to work directly from this web link, because this web link goes straight to a TIFF file, and we should be able to just quickly import our library, open this data set that's on GitHub, read the data. So this raster.io has a little format that they need to read the first band of the data, and that gives me a grid, which I can use my matplotlib plotting library to do imshow, image show. And it will just show me what my grid data is. Every different Python library has slightly different syntax, right? This src read is different than the pandas version. You just have to look at the documentation of any of these different packages to get an idea of how to work with them. But this should be exactly the same image that we get from here. If I try to visualize this in the same way, let's use even the same color map, and that image here should look very similar to this one here, right? It's doing the same visualization that is being done by QGIS. The nice thing about doing it in Python is that we don't have to go through this whole thing in QGIS of making a map layout and adding a legend and putting on our tick marks and putting on a color bar and all of these things, right? It can be a lot of work to make a map and export a map in QGIS. In Python, we can do all of these things with our short scripts. The same way that I can plot my nice rainfall data with some axes labels, and I can make the fonts bigger on my axes, I can rotate my labels and give it a title. All of these things I can also do with the image data. So, for example, one thing you might want to do is, since this is geographic data, we want to make something that looks like a map, something that can also have international borders, or it can have our latitude and longitude coordinates. When I use Matplotlib to show this image, it just has 0 to 26 and 0 to 26, right? It doesn't have the geographic data. It's just saying this is a grid of data. I can probably even just show us what this grid data looks like. Grid data. If I run this, all it is this array, right? So this is one line of data, and this is the next line of data, and the next line of data. Those are the different rows that are being shown here. So that's row number 1, row number 2. There's no geographic data there, right? It's just an array of values, which is really nice for some applications, but not necessarily if you want to make a map that you put in a report or a thesis or something like that. So there's several ways to do this in Python. One of the easier ones and the most commonly used ones is to use a mapping library that has some idea about spatial data. And the library that I'm going to use is called CartoPy, Cartography Python. It's made just for making maps from geographic data. And inside CartoPy, we also have this CRS, Coordinate Reference System. And that allows us to tell CartoPy what kind of map we want to make. Are we projecting it into UTM coordinates? Are we just using latitude and longitude? Do we want to do some sort of weird polar projection if we're working up in Greenland? CartoPy allows us to do these different kinds of projections. We can test that it's working by making a figure with Matplotlib and adding a subplot that now we have to define some sort of projection. So this plot carré is like the typical coordinate system that you might see in maps that get printed out, this sort of spherical coordinate system. And we can have a look at what this looks like by adding in coastlines. Oh, and I have to install this module. Hold on. So I followed this suggestion here when it said no module found for CartoPy, and then it gave me a little link here. To install CartoPy, click the button below, and it gave me some suggested code, this pip install CartoPy. So I put that in up here, and it seems like it was happy to download and install CartoPy for me. Did that work for everyone else as well? If you have it on if you're running this on your own laptop, you probably have it installed. It was one of the packages that was in the computer setup. But if you're in Google Colab, I guess we have to install it ourselves. Now, hopefully, we can run this line, and we get something that looks like this. So this axis, now that I've made this as a CartoPy projected axis, I have access to new commands like put coastlines or country boundaries or roads. These kinds of things I can just put on the map. By default, it'll just be a global map, but I can also, for example, add some borders and plot my Trishuli outline directly there. And now it will zoom my map to just my watershed outline. And now we can see that we have Trishuli, and this is where the border to China goes through the watershed. The next thing we want to do then is use this map data. So we want to use our grid of data and plot that also using this geographic data. So we have to do a couple of funny things here. This is exactly what we just did. We put on our borders. We plotted our Trishuli outline. I made it blue so it's easier to see on top of the rainfall data. And then I have to get some axis extents so I know where to plot my grid. CartoPy needs to know where this grid of values is actually sitting on the globe. Once we do that, we can plot it just like before, add a color bar, add some labels, add some grid lines, add a title, and we have something that looks quite nice, right? Now we have a nice map of the average precipitation over our watershed, and we can, of course, go in here and tweak things if we want to change it to 2027. We don't have to go into QGIS and make a new map layout. We can just make these small changes here, and it will quickly remake our map for us. Finally, since we now have two different Python maps, right? We have a time series chart, and we have this map. We can put them together. And we can just run both of our plotting functions at the same time. And now we get one figure, if I can zoom out here, that looks like this. And so we can put this kind of chart straight into a report, something like this. And if we want to change the dates, all we have to do is go backwards a couple lines in our code and say, start in 2022, or start in 2019. And we update our titles, and we have a whole new plot. And we don't have to go into QGIS and Python separately. We can do all of this in one place and present rainfall with the average spatial pattern to get sort of more information across at the same time. All right. So at the bottom of this, on the bottom here, I also have a few more sort of links for other places you can find data. Any kind of data that you want to plot, you can use the exact same steps. Export the time series, export the average, drop them in as these grids, and you can make a map of your own area for whatever data you happen to be studying.